An industrial worker, a concrete cutter who has spent years operating heavy machinery in massive dust clouds, arrives at a clinic struggling for every breath. His respiratory system is failing rapidly. Looking for the exact chemical cause of the damage, the medical team orders a standard toxicity blood panel. But the lab results come back completely inverted. The test detects absolutely no dangerous exposure, completely missing the actual element that is suffocating the patient. The culprit is silicon. When ingested in its soluble form, it functions as structural mortar for connective tissue. When inhaled as a crystalline mineral, it acts as a potent toxin that targets the immune cells of the lung. Trusting a raw laboratory number in a vacuum, without examining the physical environment the patient actually lives and works in, creates a fatal diagnostic blind spot. To understand the blind spot, we have to look at how humans evolved. Higher mammals completely excluded silicon from their metabolic design. We do not use it to trigger cellular signals, and it has zero catalytic purpose in our bodies. Despite this, we safely consume it every day. Plant-derived foods, like root vegetables and high-fiber grains, are rich in complex silicates. Once these grains reach the gut, commensal bacteria lower the local pH. This acidic environment breaks the complex silicates down into soluble orthosalicylic acid, allowing it to easily pass through the intestinal border and into the bloodstream. Inside the body, silicon acts purely as a passive structural gas. It slots into our connective tissues, forming hydrogen bonds and bridging the gaps between collagen fibers to provide elasticity to our bone matrices and the walls of our aorta. Because it does not enter our cellular machinery, the body processes it quickly. The kidneys act as a master homeostatic valve, rapidly filtering this soluble dietary silicon out of the blood and into the urine within 2 to 4 hours. This dietary pathway is entirely harmless. Because the element is cleared so efficiently, the human immune system never evolved to defend against silicon internally. Modern industrial practices bypassed those natural limits. Operations like sandblasting and concrete cutting apply massive mechanical force to stable quartz rock, pulverizing it into highly reactive microscopic nanoparticles. When inhaled, this crystalline silica dust is so incredibly fine that it evades the mucus defenses of the upper airway. It settles directly at the bottom of the lungs, deep inside the delicate terminal alveoli. In response, the lung deploys its localized immune cells, the alveolar macrophages. The macrophage identifies the foreign particle and swallows the debris, trapping it inside a cellular stomach to be broken down. But inside that cellular stomach, the particle fights back. Reactive silanol groups form intense bonds with the surrounding membrane, ripping the organelle apart. The cell dies, releasing destructive enzymes. The silica emerges completely undamaged, waiting for the next macrophage in a relentless death loop. This localized, continuous cell death triggers an immune panic. Surviving immune cells signal for emergency repairs, prompting lung fibroblasts to build dense, suffocating layers of scar tissue around the dust, known as silicotic nodules. This irreversible scarring is silicosis. The lung destroys its own breathing capacity in a desperate attempt to wall off dust it can never break down. This brings us back to the clinic. If the worker's lungs are packed with indestructible silica, why did the blood test miss it entirely? First, the test is looking at the wrong phase of the element. A blood panel detects the harmless, soluble silicon from the patient's recent breakfast, passing temporarily through their system. It is completely blind to the crystallized dust permanently lodged in the lung tissue. Second, standard medical equipment actively ruins the sample. The collection tubes and transfer pipettes used in most hospitals are manufactured from commercial borosilicate class. Silicon is the primary ingredient in that class. While the blood sample sits on the counter awaiting processing, silicon physically leaches from the walls of the tube directly into the liquid, artificially inflating the concentration. The very container chosen to hold the objective medical evidence ends up framing the patient for a chemical toxicity they do not have. Even the highest-end testing equipment faces biological limitations. This data visualization shows an inductively coupled plasma mass spectrometer at work. It vaporizes the blood sample at 8,000 Kelvin, sorting individual atoms strictly by their atomic weight. For silicon, it isolates a mass of exactly 28. But the machine constantly pulls in ambient air from the laboratory. In the extreme heat of the plasma torch, 2 nitrogen atoms from the atmosphere fuse together into a polyatomic dimer. Each nitrogen atom weighs 14. Bound together, they weigh exactly 28. The machine cannot tell the difference between the true silicon atom and the fake nitrogen dimer, counting room air as a toxic heavy metal. To correct this, technicians use kinetic energy discrimination. They flood a collision chamber inside the instrument with helium gas, creating a microscopic obstacle course. Because the nitrogen dimers are physically larger, they violently crash into the helium and lose forward momentum. The mass filter screens out the slow, bulky dimers, allowing the sleek, single silicon atoms to slice straight through to the end. Yet, even with advanced physics filtering out the room air, the blood test is still only analyzing dietary ghosts and glass contaminants. Diagnosing true silicosis requires matching high-resolution chest CT scans with a documented history of the patient's occupational exposure. Biological architecture and environmental context cannot be separated. True diagnostic stewardship requires treating the physical reality of the patient's life, rather than relying exclusively on the numbers printed on a compromised lab report.